So let's see an example of that. So let's say we have a molecule like this. Cis 1,2-dibromocyclohexane. And let's do the flip chair. Oops. So there's the flip chair. It's hard to see the plane of symmetry here, because both of these conformations don't look like they have one. In fact, they probably don't. If you look hard enough, you probably won't find it. But what I want you to do is I want you to take the average between these two, which would be the planar version of this molecule. So instead of considering it like this or like this, consider it like this. And now the mirror plane, I think, is very easy to see. So this molecule is not chiral. It has a mirror plane when you lie it flat. So therefore, you would consider this to be not chiral. Now you can do the same thing with the trans version, right? This one is indeed chiral because it doesn't have a mirror plane. So just when there's conformations at equilibrium, just consider the 50% version, the in-between version, which in the most cases that you'll see, it's cyclohexane or cyclopentane or some kind of cyclical molecule. Just think of the molecule in terms of it being flat, and that makes life a whole lot easier for you. All right, in the flat version, it's achiral because there's a mirror plane. In this version, it is chiral because there is no mirror plane, and that's how you should do it. That's the easy way. Fischer projections. Now, Fischer projections are a great way of viewing chiral molecules, but you have to know what it means. You have to be able to examine it and in your mind's eye or just draw it out, what does it mean in a Fischer projection. So a Fischer projection is going to look at a molecule from this point of view, more or less. Okay? This point of view, more or less. Now, it's hard to see it on a flat surface. If you have a model kit, it's much easier. But if you don't have a model kit, do your best to follow along. So now, when you're looking at it through this point of view, your hydrogen will be on your left. If you're standing here, let's just draw us here. So we're standing here with our top hat. And we're looking through here. From our point of view, this hydrogen is on our left. From our point of view. This CH3 is pointing down. CH3 is pointing down. The OH is to our right. And the CH2OH is down, but it's also in front of us. It's down and up. So that's how we're looking at it. Let's do that again. Let's just get rid of all this noise and let's do it again. So we're standing here. There we are. And when we look through this carbon atom right here, the first thing we're going to notice is that coming towards us is an OH on our right and a hydrogen on our left. From this point of view, there's an OH coming towards us and a hydrogen coming towards us. The OH is on our right, the hydrogen's on our left. They're drawn as wedges, so they're coming towards us. Hydrogen is on the left, oxygen, or OH, hydroxyl, is on the right. Okay, so let's get rid of that. Now, from this point of view, we look down at our feet and we see this CH3 group. So the CH3 group, from our point of view, is going away from us and it's down towards our feet. So if we're standing here, The methyl group is down towards our feet or down to the bottom. This CH2 group is up, is facing the top of the page, but it's also going into the page. It's down from this point of view. Now this is a side-on view. This is more or less, so the side looking straight into this carbon, so it's a side view. This is a view looking straight down on the carbon between the hydrogen and the OH. I know that's confusing. A model kit will help you here. So now, this is what it looks like from this point of view. Fischer goes one step further. Instead of having the carbon, wedge, wedge, dash, dash, Fischer gets rid of that. And he also gets rid of the chiral carbon. Notice how there's no chiral carbon drawn here, but the other carbons are. In a Fischer projection, the chiral carbons are not shown. So there's a carbon here. Anything that's drawn to the right and to the left is up. So Fischer just wants you to know that. Fischer just wants you to know that anything drawn on a chiral carbon to the right and to the left is up, coming towards us. Anything drawn from the chiral carbon up or down is going away from us. So this is coming towards us. How do I know? It's on the right-hand side of the chiral carbon. This is coming towards us. How do I know? It's on the left-hand side of a chiral carbon. This group is going into the page because it's on the top. This group is going into the page because it's on the bottom of a chiral carbon. That's how it works. All Fischer projections do this. They all assume you know that. Now, I know it's a lot to assume, but once you get the hang of it, you're going to like Fischer projections, because once you start getting more than one chiral carbon, things can get real hairy real fast. So this is some stuff to write down. Fischer projection is a flat representation of a 3D molecule. The chiral carbon is at the intersection of the horizontal and vertical lines right here. So that's a carbon right there. It's the chiral carbon. Horizontal lines are coming at us. Vertical lines are going away from us, or behind the line, behind the plane. And here's just another way to look at it. So we're viewing it from this point of view right here. So number 1 and number 4 will be towards us and to the left and right of us. 2 will be on top and going away. 3 will be on the bottom and going away. It's all about perspective from right here. Okay, it's all about the perspective from this point of view. So we're standing here. As we're looking into there, carbon, the group number 1 is coming towards me on my left. Group number 4 is coming towards me on my right. Group number 2 is up but away from me. Group number 3 is down and away from me. From this point of view. A model kit is helpful at this point. Fischer rules. The carbon chain is on the vertical line. So the carbon chain is on the line running up and down. The highest oxidized carbon is always on the top. So the carbon that has the most bonds to oxygen is on the top. It could be some other way, but it's almost always bonds to oxygen. You can rotate a Fischer projection 180 degrees. So you can rotate a Fischer projection 180, but you cannot rotate it 90. That is not allowed. 180 degree rotation, perfectly fine. 90 degree rotation, perfectly wrong. Just always wrong. Don't even do it. And here's why. So let's take into account this molecule right here. Now, this hydrogen's coming away from us, going towards us. This OH is going towards us. This carboxylic acid is going away from us, and the methyl group is going away from us. Now, let's assign priority groups to this molecule here. 4, 1, 2, and 3. 1 to 2, 2 to 3, and then back to 1. So let's do it on this one. 1, 4, 2, and 3. 1 to 2, 2 to 3, and then back to 1. 1 to 2, 2 to 3, then back to 1. Now, you would think And I understand why you would think this, that this is S. Because if I have my little thing and I'm doing a little trick, 1 to 2, 2 to 3, back to 1, I'm doing that little trick I taught you, you would say, that's S. But it's not, it's R. Oh, I know. I blew your mind, right? Well, it should be S. Why is it changing? It's not changing. The rules don't change. What's happening in a Fischer projection is the low priority group is not facing away from me. It's facing toward me. See how that group is up, not down? Remember, in Kahn-Ingold Prelog rules, the low priority group is supposed to be facing away from you. Now, you don't have to redraw this. In fact, don't redraw it. Just remember, if the hydrogen is coming towards me, the configuration is the opposite of what I think. 1, 2, 3. I think it's going to be S, but the hydrogen is coming towards me, so therefore it must be R. Oops. So don't freak out. Don't freak out. It's because that priority group 4 is coming towards me. That's why it's not S. Even though when we do our little 1, 2, 3 trick, if I'm turning the steering wheel that way, I'm certainly not going to the right, but that's because of this priority group being the wrong direction. That's all. That's the only thing that's happening. Let's go over here. Do the same thing. 1, 4, 2, 3. 1 to 2, 2 to 3, and then 3 back to 1. Appears to be S, but remember group 4 is pointing up, so this is R. So by rotating a Fischer projection 180 degrees, it doesn't change the R or the S. And that's the key. It does not change the R. It does not change the S. So it was R here, rotated at 180. It's still R. It's still R. Now let's take that same Fischer projection, rotate it 90 degrees, and see what happens, and see why it's forbidden, why you can't do it, or why it's wrong when you do it. So here's our original Fischer projection of a molecule with an R configuration. Now let's rotate this thing 90 degrees. So I'm going to move it, say, this way. Everybody's going to change positions 90 degrees, okay? When I do that, the COOH will go here, the OH will go there, the CH3 goes here, and the hydrogen goes here. Now you may be thinking to yourself, well, what's the big deal? What's the big deal? It's just rotate it, no big deal. You have to remember what Fischer means. You have to remember what Fischer means. So this molecule would actually translate into this. Whatever's on the top and on the bottom are going into the plane. Whatever's on the right-hand side and the left-hand side is going towards us. So this will be COOH here, and methyl group will be here. Put in priority numbers 1 and 4, 2 and 3, 1 to 2, 2 to 3, and then back to 1. This is indeed S because now look, low priority group number 4 is in the back. So it's the correct way. It's where it's supposed to be, right? So now the low priority group's in the back. This appears to be S, and the low priority group is back. So it is indeed S. So what you've accomplished by rotating a Fischer projection 90 degrees is you've accomplished drawing the enantiomer. So by rotating it 90 degrees, you've actually changed the molecule. You've changed the absolute configuration, or the R and the S. You've changed it. So you cannot rotate Fischers 90. You can only rotate them 180. That leads us to diastereomers. Now, diastereomers are molecules that have 2 or more chiral carbons. And once you have 2 or more chiral carbons in a molecule, you have the potential for diastereomers. You may not have any. You may have enantiomers, but you could have diastereomers. Diastereomers are stereoisomers that are not mirror images. Now let me draw you an example of that. Let's draw say this molecule here. So bromine, and let's put a chlorine here. So there's a bromine and a chlorine. 2 chiral centers. So there's a chiral center here and a chiral center there. If I drew this molecule, you can see that these molecules are definitely related to each other. They're definitely related. But they're not enantiomers. They're not mirror images, first of all. That's the first thing. They're not mirror images. They look like they might be, but they're not. Take a real close look, and you'll see they're not mirror images. So therefore, they're not superimposable either. Like, there's no way they're superimposable. Because if I pick this thing up, move it over here, try to superimpose it, the chlorines are facing the wrong direction. So those are called diastereomers. They're stereoisomers that are not superimposable and not mirror images. Okay? Non-superimposable, non-mirror image, diastereomer, and not constitutional isomers. Notice the carbon skeleton and all the bonds are the same. The only thing that's different is the orientation of that chlorine in three-dimensional space. That's it. So these are diastereomers. There we go. So when a compound has 2 or more chiral centers, you have the possibility of getting what are called enantiomers. We know about those. They're non-superimposable mirror images. Diastereomers, non-superimposable, not mirror images, not constitutional isomers either. Or meso. We haven't talked about meso yet. We'll get to meso in a minute. We've seen examples of them, but we just haven't identified them. Diastereomers have some matching and some opposite configurations at the chiral carbon. So the first example I showed you, the bromine was the same in both cases, same R or S. We didn't assign it, but it had the same orientation that was coming towards us in both examples. The chlorine was going back and was coming forward. The one on the left was going back. The one on the right was coming forward. So that's where the difference was, and that made them diastereomers. Now, before we get to it, a meso compound has an internal mirror plane. So it has 2 chiral centers, or 3 or 4 or 5, or 6 or 7 or 8 or whatever it is, but they have an internal mirror plane which prevents them from being chiral. Okay? Prevents them from being chiral. Now, there's a fun rule you might want to write down and remember, the 2 to the n rule, where n is the number of chiral carbons. That's the maximum number of stereoisomers you can get. So let's take, for example, a molecule that has 1 chiral center. So there's a molecule with 1 chiral center. So n equals 1, because n is the number of chiral centers. So 2 to the 1 equals 2. 2 to the 1 equals 2. No problem. Enantiomers, right? R and S. That's it. But what if we have a molecule that has 2 chiral centers? So now n equals 2. So 2 to the n equals 2 to the 2 equals 4. So now there's potential for 4 different stereoisomers. Okay? 2 chiral centers, 2 pairs of enantiomers each. So a total of 4. Let's see an example. What if we had something like this, where there's an OH here and an OH there? And now there's potential here for 2 to the n, where n equals 2, because there's 2 potential chiral centers, right? 2 to the 2 is 4. So there's 4 potential stereoisomers. Let's draw them. There we go. Let's draw the mirror plane. Or not the mirror plane, the mirror image. There we go. So there is this one and this one. Now, I know they look the same. I know they do. I want you to try to superimpose this one on top of that one. And you'll find very quickly you won't be able to do it. It looks like you should be able to, right? It looks very simple. Just rotate it and flip it upside down. No big deal. Oh, it doesn't work. This and that are not the same. They are not mirror images. These two things are enantiomers. All right, so notice I took the flat molecule and I put one chiral center with the OH up and one with it back. I could have done both forward or both backward. It doesn't matter how you start, just as long as you start. Now, what you do now is you take one of those chiral centers, just one of them, not both of them. Take one of them, pick one, doesn't matter if it's this one or that one, makes no difference, and invert it. What I mean by that is, if I'm going to take this one, it's coming towards me, invert it means make it go away from me. So inversion means make it go the other way. This one's coming up, so I want to make it go back. So when I redraw the molecule, there we go. So now this one's going back. Now notice this one didn't change. You can only change one at a time. Don't start changing 2 or 3 chiral centers at once. You'll confuse yourself and you'll get it wrong. This one's going forward. Now it's going backwards. This one's going backwards. It repeated itself down here. Now, draw the mirror image of that one. Now, this, I think everyone's picking up on what I'm doing here. This is the same as that. If you pick this one up, just pick it up and plop it over here. You'll see that these two things are exactly the same. These are not enantiomers. These are meso. These ones are meso. These ones are meso. Now, I could have predicted that by the fact that there's a mirror plane right here, but I didn't want to spoil the fun. I didn't want to spoil the surprise. There's a mirror plane right there that reflects one chiral center onto the other. So this is not chiral. The black molecules are not chiral. Those are achiral because there's a plane of symmetry. So these are what they call meso. Okay? Now, let's clean up the drawing here a little bit. Let's call this molecule A, molecule B, molecule C. A and B are enantiomers. C and A are diastereomers. B and C are diastereomers. Okay, so we have A and B, which is a pair of enantiomers. C and A are diastereomers to each other. B and C are diastereomers to each other, but they're all related. They're all stereoisomers in the same, if you want to say it, family. Okay, so when you have 2 chiral centers, you have the potential for 4 stereoisomers. In this example, we only got 3 because one of the stereoisomers was meso. That happens. Let's see another example where that's not the case. A little more, I wouldn't say tougher, just different. Let's do Fischer projections this time. There we go. So there's one Fischer projection. There's 2 chiral centers, so n equals 2. So 2 to the n equals 4. So there's 4 potential stereoisomers. No problem. Draw the mirror image of the first one. Bromine here, H there, and H there. So there's the mirror image. So those 2 are enantiomers to each other. Let's take the blue one, and let's take the top stereo center, and we'll just invert it. So in a Fischer projection, when you're inverting, the bromine goes from here to here, and the hydrogen goes over here. Just take the bromine, erase it, take the hydrogen, erase it, and put them in each other's location. So the bromine is going to go here, the hydrogen is going to go there. No problem. Let me draw it for you. So the hydrogen will be here, the bromine will be there, and then the bottom one Let me just circle it real quick. This one didn't change. Remember, don't start changing 2 or 3 chiral centers at once. Only change one at a time. So now, let's draw the mirror image of this one. And there we go. So this and that are mirror images. They are not the same. They are mirror images that are non-superimposable. So let's call this A, B, C, and D. So these are my 4 stereoisomers. Like I predicted there before, there are indeed 4. So A and B, comma, C and D are enantiomers. So A is an enantiomer to B, B is an enantiomer to A, C is an enantiomer to D, D is an enantiomer to C. Just like that. Those are enantiomers. Now, A is a diastereomer to B, or sorry, C, and A and D diastereomers. B and C and B and D diastereomers. And that's how they're all related. So in a grouping of stereo molecules, enantiomers and diastereomers, if you're not an enantiomer to something, you're the diastereomer to it. Okay? Because every stereoisomer can only ever have one enantiomer, but you can have numerous diastereomers. And that's how it works. That's how this system works, and that's what diastereomers are. So, enantiomers, non-superimposable mirror images. Diastereomers, non-superimposable, non-mirror image, but not constitutional isomer either. So you can't change this. You can't change the skeleton. It has to be the same bond, just different orientation in space. Or your meso. Meso means you have a mirror plane. You have two or more chiral centers, but you have a mirror plane that makes it non-chiral. All right, guys. So with that, that's the end of the stereochemistry chapter. I hope you had a good time. Hope you learned a lot. And with that, I want to say, you know what? Good luck and good chemistry. We'll see you soon.